Imagine a universe built on simple switches. These switches can be either on or off. This is the world of digital electronics. We represent these on-off states with ones and zeros, forming the binary language. That's where logic gates come in. They are the fundamental building blocks of digital circuits. Let's meet some of these gatekeepers of the digital realm. First up, the AND gate. Imagine two doors that must both be open for you to pass. That's the AND gate. It only outputs a 1 if both inputs are 1. Next, the OR gate is like a single door with two handles. If either handle is pushed down, the door opens. The OR gate outputs a 1 if at least one input is 1. The NOT gate is a rebel. It takes a single input and flips it. If the input is 1, the output is 0, and vice versa. Then we have the NAND, NOR, and XOR gates. These are like the AND, Oregon, and XOR gates, but with a NOT gate attached at the output, inverting their results. They add another layer of control to our digital toolbox. Now imagine trying to design a complex circuit with hundreds or thousands of these gates. It would be a nightmare to keep track of everything. That's where Boolean algebra comes in. Named after the mathematician George Boole, this system of mathematics uses variables and operators to represent logic circuits. We use symbols like plus for OR, a dot for AND, and a bar over a variable for NOT. Boolean algebra provides a powerful way to simplify complex logic circuits. For example, the identity law tells us that a plus 0 equals a. This means that any input OR'd with 0 will always be equal to the original input. Similarly, De Morgan's theorems provide rules for converting between different gate combinations. These theorems are like mathematical shortcuts, allowing us to simplify expressions and optimize our circuits. By applying Boolean algebra and simplification techniques, we can take a messy jumble of logic gates and transform it into a clean, efficient circuit. This is like taking a long, complicated sentence and rewriting it to be clear and concise. One powerful tool for simplification is the Carnot map. It's a visual method for minimizing Boolean expressions, making it easier to design and understand complex circuits. Logic gates and Boolean algebra form the bedrock of digital electronics. From the smartphones in our pockets to the spacecraft exploring the cosmos, these fundamental concepts power our technological world. By understanding these building blocks, we unlock the secrets of the digital age and pave the way for even more incredible innovations in the future.